Okay, so welcome to another class about the Branch spaces, and today we will talk about one of the very nice results in theory of the Branch spaces, which is the characterization of the space. Okay, so far I give you a function E over init class, and you can build the Branch space H2 or even HP. And one of the nicest things is that you can, there is a converse statement, which is give me a Hilbert space with of entire functions with certain properties. Then I can say, well, then this must be the Branch space associated with some function E. Okay, and that is the main result of this class. And so theorem 23 from the book. So let's H2 just be any Hilbert space okay, which the members of this Hilbert space, the vectors, are entire functions. Okay, F with norm given by some kind of inner product. Okay, so it's a Hilbert space, and imagine you have a collection of functions F, which is a vector space. So you can add in functions and you can multiply by complex scalar. And you put a norm in that, whatever that norm is. And it turns out that you get, this norm is given by an inner product, and it turns out that you get a Hilbert space, okay? So suppose you have something like that. Assume further that, and then we have three hypotheses. The first is that, okay, it's just a technical problem. So now, so we have this first assumption, if F belongs to the space and F is 0 at some non-real point, then G, which is the function, you cut the 0 of F, so you divide by Z minus W, but then you put the 0 in the other half plane, puts that bar, W bar, okay? So define this guy. Then the claim is that, the assumption is that this guy will belong to the space, okay? And have the same norm. Okay. Second hypothesis, which is the following, which I think it should be the first because it's the most important. The functional F that evaluates evaluation function is bounded in the space. Which is the same to say that this is a reproducing kernel Hilbert space, because this would automatically imply and also be equivalent to the existence of some kernel that realizes this evaluation of functional. And the third hypothesis, which not so much needed, we will see later, but helps, if you don't assume 3, then you get something else which would not be a the Branch space, but would be isometric and isomorphic to 1. But if you put 3, then everything works out nicely. 3 is if F belongs to the space, then F star also belongs to the space and has the same norm. Okay, so suppose you have a certain Hilbert space of entire functions with these 3 conditions. Then the claim is that exists some function E, or mid-pillar, such that this space is just the Branges space as we constructed, associated with this function E. Okay. So before we start, I want to make a remark. In a sense, the Branges spaces, I mean, in a very precise sense, the Branges spaces are the spaces, Hilbert spaces of entire functions satisfying these 3 hypotheses. Okay. Because it's easy to see that a Branges space does satisfy these 3 hypotheses, because the norm is always some integral, L2 integral on the real line. So, and if you recall the definition of the Branges spaces, which is to take the function, divide by the function E, and ask it to be a bounded type. So if you divide by E here on both sides, this bit would be a bounded type, and this is also bounded in the upper half plane, and therefore this bit would be a bounded type, and you can compute the mean types, and the mean type of G over E will be equal to the mean type of F over E, for instance. And you do the same with the star. So it's easy to see that the Branges space does satisfy property H1. The H2 is obvious because we have a reproducing kernel. And H3 is also obvious because the norm, well, this is always true because the condition being the Branges space is symmetric in terms of taking star. And we know that the norm is the same because on the real line, these functions have the same moduli. Okay, so that's the beauty of the theory, because it characterizes completely the spaces. Like, you're not asking too much. If you think about the condition of being a reproducing kernel Hilbert space, well, most of the spaces of analytic functions, most of the Hilbert spaces of analytic functions which are interesting, they all are reproducing kernel Hilbert spaces. So you're not asking too much here. I mean, you need something to work with, and you need a kernel. So this is not asking too much. The first condition, well, the third condition I said already could be removed, and then you end up with a space which will be isomorphic, and we'll comment that in the end. But the first condition is what is telling you that the norm on the space is really some kind of norm on the real line, some kind of evaluation, an integral on the real line, because you are moving the zeros of F. You're taking a 0 in the lower half plane and putting it in the upper half plane, or vice versa, and the norm is not changing. Okay, so you can basically like move all the zeros up, and the norm is still not changing. Okay, so this will characterize this will tell us that the norm is some sort of an integral on the real line. Okay. What else? Yes. So let's see the proof. The proof is not hard, but it does assume that you have solved certain problems. Again, I'll explain what those problems are and what the claim is, and then we use them to solve to prove this. Okay. So so H2, which is we have the evaluation of function is bounded. It clearly implies by Green's representation, the famous theorem you see in functional analysis, that since it's continuous, it has to be given by the inner product against a function, kw, okay? And so this function kw is the reproducing kernel. Which is the reproducing kernel. Of H2. Okay, great. So since we have a reproducing kernel, I want to know, I will have to evaluate kWw at some point. So I want to know exactly when this is strictly positive. So the claim is that kWw, which is the norm of kW squared, is strictly positive if W is non-real. Okay, that's the claim. Okay, why this is true? Well, suppose that it isn't. Well, if kW is identically 0, which is the same to say that kWw is 0, for some non-real W, then we know that Fw is 0 for every F in the space. Okay, and W is non-real, so therefore, so by H1, I can remove that 0 and put it in the other half. Okay, and that function will belong to the space. Okay, but then you can kind of see the problem already. Well, this function belongs to the space, and just remove the 0 at W, but any function in the space has to vanish at W. So therefore, this function has to vanish at W. So that 0 that you removed is actually of order 2, and so on. So that would imply that F vanishes, I mean, apply after via applications, several applications of H1, F vanishes. Inductively, you conclude that F vanishes at Z equals W with infinite multiplicity. And therefore, no analytic function can satisfy this property. F is identically 0. So H2 is the trivial space. Okay? So I should say in the beginning that H2 is non-trivial. So let me put here. So this non-trivial should be a non-trivial Hilbert space. Okay, so since it's non-trivial, then we have this with a contradiction. So we know that kWw is greater than 0 for every W which is not real. Great. So what I want to do now is the following. Yes. Yes. Okay, so now what I want to do, let me do that later. I want to leave that in the moment. Now what I want to do is actually solve one of the problems that I ask you to solve So we'll help you out because I decided that it's really would be really great if you have an idea why we will do certain computations. Okay. So recall that we are aiming to something. We are aiming to show that KWZ is EZ EW bar minus E star of Z E of star of W bar divided by 2 pi I W bar minus Z. Okay, put interrogation here. That's what we're aiming for. Okay. So, so for some function E, so I want to know if I can write the kernel in this way. Okay. If I can write the kernel, so note that if this is true, for some entire function E, okay, if that is true for some entire function E, then I just evaluate KWW, okay, in the upper half plane, and that would be what? EW squared minus moduli of E star W squared divided by what? Divided by 4 pi y if W is X plus IY. Okay, but this is positive. Okay, so if Y is positive, that implies that EW is greater than E star of W for W in the upper half plane. So that would imply that E is Zermit-Pilar. Okay, so this space exists. Okay, and the reproducing kernel associated with E, well, we just showed, is that by assumption is identical to the reproducing kernel K of H. But since the span of KW, let's see, KW dot for W in, let's say, C+, we don't care as long as it's like an open set. I made this comment in the last class. This is dense. I don't need, I can put all the complex plane. I don't need that. This is dense in H, of course, but this is equal to the span of, well, it's the same as the reproducing kernel associated with E. And this is dense in H2 of E. So this thing implies that H2 and H2 of E coincide in a denser sense in a dense set. Not only that, because in this set, if you take the norm of any function in there, it will be just evaluations of the reproducing kernel. And so therefore the norms would agree. Okay, because in the end, the norms would only be just things like K alpha beta for some alpha beta. But since they are the same, they agree. So they coincide in the set with equal norm. Okay, and whenever you have something like this, they have to be equal isometrically. By a simple limiting procedure, any function in the space should be in the order space because the spaces are complete by assumption. H is complete by assumption. The H2 is complete because we showed. And then by simple limiting procedure, you can show that they're equal. Okay, so that would finish the proof. So we only need to show this thing. Okay. Let me put like a, oops. So we only need to show star. Okay, so how can we show star? Okay, so so there is a series of problems in the book, and the series of problems is saying that, well, suppose you have a reproducing kernel like this, KWZ, and it satisfies certain identities. Okay, and then the problem claims that, okay, then you can write it in this way. Okay, then you can write it that way for some function, for some entire function E. In fact, the book writes this thing, the problem asks to write this, but using the formulas involving the functions A and B, and the series of problems to show that these functions can be assumed to be real entire, and then you can write it in this form. Okay. So that's the problems in the book, and then but basically what you have is the kernel satisfies a certain identities, let's say 2 identities, and therefore you can write it in this way. Okay, so I want to give you a sense why these identities should be true. Okay, so let me define 2 functions. So okay, so to show that, so now define these guys here, which will be, so LWZ would be 2 pi I W bar Z KWZ. Okay. So that should be, we don't know that yet, but that should be just this function here. Oops. Okay. So the question is, how to write E in terms of L. Okay. If you can write E in terms of L, then you should say, okay, that's my candidate for the function E. Let's show that it works. Okay. So let's see what kind of identities L should satisfy. Okay. So if L was of this form, and then I do this, what I will get is a product, which I will write explicitly here. Maybe let me do just the first, and then the second I write it directly. So that, let me put always an interrogation here, once we don't know. Then we have to multiply by the other bit. Well, this is supposed to be W. Yes, this is W. Okay, so if you multiply term by term, then what you get is, well, the first one you get E alpha squared, and then EZ EW bar, then you get, so this is this guy times this. Now let's do this guy times that. That'll be plus e star of z, e star is alpha, and then you get, oh, then we have a star moduli. So you have e star of alpha moduli squared, because we have this bit and this bit. And then we have e star of c and e star of w bar. And then the other terms you can compute, and they are e alpha bar, e star of alpha, e of z, e star w bar, and then minus e star of z, e w, e star alpha bar, and e of alpha. Let's see if these things make sense. So this is supposed to be what? This guy times this. Yes, and this is supposed to be this guy times that. Yeah, okay. This is what we get. So then now let's do the same, but put alpha, change it by alpha bar. And then you see that you have a certain symmetry, and then you will be able to have a certain cancellation. Okay, so if I change alpha by alpha bar, this first term here is equal to this. And then z stays the same. And this other guy changes to e alpha squared. This guy stays the same. And these two here merely flip, because if I change alpha bar here, this will become e star, and this will become e alpha bar. So this guy just flips. I mean, stays the same. And also these guys here. So this becomes E alpha. Yes, and this becomes E star of alpha bar. Okay, so great. So if you factor them out, if you make the difference, so if you do I minus II, what you get is we'll be able to isolate this term here. And then you will get EZ EW bar minus E star of Z E star of W bar. You should put interrogation and all those things. Just to point out that we're trying to come up with an identity. So this guy should be L again, because that was our definition of L right in the beginning here, which should be equal to that guy. Okay, so and this bit here is what? This is L of alpha alpha, or minus L of alpha bar, because if you change alpha by alpha bar, just flip it. Okay, so that implies the following inequality. So if what was L of I? So L I was this. So if I divide by L alpha alpha, and then I subtract II, which will be this guy, and I divide by L alpha alpha, this should be LWZ. Okay. But L alpha alpha is also equal to L bar here, and then you put the plus here. Because when you change alpha by alpha bar here, it just flips. It's simple computation, just flip this two, and then you get minus what you had before. So this is the inequality identity we want to prove, okay? So the problem says, and this would be the content of problem 51. So what we just showed is problem 51, okay? So this is problem 51. Okay, problem 51 is to show that in any de Bruijn space, you have this identity for the function L defined from the reproducing kernel by this way. Okay, so that was problem 51. So, okay, so we want to prove that, okay, that would be the fundamental bit that will allow us to write the kernel as we want. So by problems, and now we use the problems, so by, I guess it's problem 52. Well, to use problem 52 and 53, I need an extra bit, okay? What I need is the following. So now, so far I didn't use hypothesis 3, okay? So now is the point that I will use hypothesis 3, okay? So, oops. Okay, so how can we use hypothesis 3? Now I have to go back. Okay, so now let's, I want to get another identity for the kernel. So now we use H3. Okay. So we just proved problem 51, but problem 52, I will say in a moment what problem 52 and 53 are. But to apply them, we need to do some work with hypothesis 3. Okay. So what hypothesis 3 is saying is that what is, let me recall, is that F star belongs to the space and it has the same norm. Okay. Well, that implies, that's equivalent, this is a Hilbert space, is to say that the operator star is unitary. Okay, so it means that it preserves the inner product. Okay. So what you can do is the following. What you can do is wait, 1, 2. Yeah, so there is a calculation here to be made. Calculation here to imply this is true, and this the usual thing we do is just you write f of t moduli squared and also f of minus ig moduli squared, and you know that this has norm equals to this, and you know that this guy has norm equal to this. Okay. Wait, is that? Oh no, this. Sorry. So what I said was wrong. There is a one lighty bit. This implies that this with a bar. Okay. Yeah, so it's not that the operator is yeah, so let's think in terms of the de Bruijn space. Why this is true? So what I said before was wrong, actually. So why this should be true in the de Bruijn space? Well, because usually what we do is this. That would be the inner product. Okay, if I put star on both sides, that would be what? That would be this. times this, okay, which is bar of the inner product. So this is FG, and this is F star, G is star, with bar. Okay, so in the Bern space, that's what they call, that's what identity we have. So we have to show this. So therefore, the way to do it is this: you write these two identities, okay, and then you open them using that this is the norm squared of the first function, norm squared of the second, minus 2 times the real product between the first, the real part of the inner product between F and G. And you do that for both those terms. And then the part when you just have the norm of F and the norm of G, that would be equal to the norm of F star and norm of G star. So in the end, you end up only with some identity involving the real part of the inner product, and in the second one, the imaginary part of the inner product. And then you add those and you conclude this, okay? So this is what you should use in here, okay? So if that is true, then what you can do is that you just, so if I take, so I want to know what's the star of the kernel KW, okay? So I have the kernel KW and the star in the variable Z. Okay, to know that, basically I just have to know what's the inner product with any function F. Okay, well, if that's the case, then I can move the star to the other side by the previous identity and put a bar, okay, by using this identity here. So I'm using that, I can write this as a star, and then I move, then I apply the identity and I get that. Okay, but this is then just evaluation F star, a W and bar, which is just FW bar. But this is also just F KW bar. Okay, but since this is true for any function in the space, it implies that KW star equals just KW bar. That is KW Z bar is just KW bar Z. Again, a property that it is satisfied by a kernel in the Bern space. Okay, so now we can apply problems. Now I can apply problem 52 and 53. Okay, so what they say is that whenever you have a reproducing kernel, wait, should I? Yes, so what they say is whenever you have, so what they say is that if KW star equals KW bar and L satisfies double star, which would be this identity here, okay? So we do know the first condition, we just don't know the second yet. We do know that the second holds for any of the Bern space, but we don't know if it holds for this Hilbert space H given. But this one is, we do know, we just did it, we use it, condition H3. But if we have this, then K equals the KE for some function. Okay, it could be just for an entire function. If this is true, then E will end up being Hermite-Pillar anyway. We saw that. So that's the conclusion of problem 52 and 53, okay? Which is for you to figure out how we can, from these two inequalities, this one, identity, sorry, this one and identity two, to come up with a function E. So what I will do now to finish the proof is I will show that identity 2 stars here is true. And therefore you can apply problems 52 and 53 to conclude that we indeed have a Hermite-Pillar function satisfying things, okay? And just a hint to solve these problems, it's more or less a bit more difficult, but more or less the same thing we did when we characterized the L-phi spaces. Recall the L-phi spaces we did. In there, we also defined an L-phi given a phi function, and also the second result was to characterize an L-phi space by certain conditions, okay? And in there, we had to extract the function phi. In a similar way, you have to do this thing here, okay? Okay, so let's show now. Now, it is enough to prove double star is true in H, in this given space, okay? So let's show it is true. Okay, so I need some auxiliary functions. So let me define f alpha of wz to be kwz minus k alpha z kw alpha divided by k alpha alpha. So you can already see that I'm getting the intuition from the calculations I did, like this form here, to prove the identity I want. Okay, so what is that function? This function, so note that well, f belongs to the space for each, let's say, I should put the w dot here. Oh, and I should say where these guys are. So, so alpha and w are just complex numbers, but not real. And z could be anything. Okay, we'll keep that in mind. So for each alpha and w, well, we just have the reproducing kernel, which is on the space. As a function of z, we just have this, which is also a function in the space. And this is just a constant. And this guy here is non-zero because alpha is non-real. And we just showed that k alpha alpha is not zero. It's greater than zero, by the way. Great, so that's the function in the space. And moreover, it vanishes at alpha. Because if I just evaluate, in here I will have k alpha alpha, which we cancel with this. So I would get kw alpha and also kw alpha here. So it's 0. Okay. 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 So I want to investigate what happens. So I can, for instance, so now by H1, I know that the function g alpha, which I will write as g alpha, where I cancel that 0, okay, times f alpha wz, also belongs to the space. And moreover, now it vanishes at alpha bar. Okay. So what I want to compute the inner product between F alpha and J alpha. Okay, so let me do that in general. Okay, so suppose we have two functions u and v in the space. U vanishes at alpha, v vanishes at alpha bar. Okay, these are non-real, so you can imagine like u being the function f alpha and v being the function g alpha, for instance. Okay. So I claim that T alpha u, I will tell you what T alpha u is in a moment, equals u T alpha bar v, where T alpha is the operator that takes the g, or any function f, let's say, into z minus alpha bar, z minus alpha, f of c, if f of alpha is 0. Okay. Okay. So so it had a function u. So that's the situation we had before with this function f alphas. U was the function that vanishes at alpha, f alpha. So it could apply this T alpha, and then T alpha f alpha, by what I just wrote, is just the function g. So it could maybe, right, this guy here is just equal, also equal to T alpha f alpha. Okay. So computed inner product with G alpha and F alpha is basically just doing this bit here. This would be G, and this would be, yeah, this would be G, and this would be any other function that vanishes at alpha bar. Is that what I want to do? Yes. Okay. So that's what my claim. So this is saying that, this is basically saying the dual of this operator is just T alpha bar. Okay. The dual is not, well, the operator is not defined the whole space, by the way, because it's only defined the space where f is 0. Okay. But so that's, so it should put like that's okay. Okay, so how can we show that? Well, it's basically the same trick I did for the F star operator. We know that 0 equals T alpha u plus v squared minus, well, so no, so u vanishes at alpha and v vanishes, oops, and v vanishes at alpha bar. So when I apply this, this function vanishes at alpha bar, and this function vanishes at alpha bar. So I can apply the operator T alpha bar on both. And by hypothesis 1, they have the same norm, so this is 0. So this was H1. Okay, but we can rewrite this term here because T alpha bar composed with T alpha is just an identity. So this bit here is just U and then T alpha bar applied there. So this is just this. Okay, and this is bar, sorry. So now we can compute, we're going to have this here at some point, and then minus this, which will cancel. The same with the v. So in the end, we only have the real part. So this would be like 2 times the real part of T alpha u v minus u T alpha bar v. Okay, so I'm saying that the real part of these things coincide. Okay, but in the same way I can do with plus iv, okay, squared minus, and this would be twice the imaginary part of T alpha uv. My v looks like a u minus u T alpha bar v. Okay, so this whole bit implies that T alpha u v equals v, oh, sorry, u T alpha bar. Okay. So knowing that, I can use that for my functions. So what I want to do is to do T alpha, which was a function g, so right, I want to write g alpha of wz times, and I would do it with alpha bar because I know that f finishes at alpha, so therefore f will finish at alpha bar, and that will be in the form what I just did. And here I will even put another number, beta, instead of w, and just another thing. Okay, so to be rigorous, I should like put the point here. And that is just T alpha of F alpha of W dot, and then F alpha bar of beta dot. Okay. By definition, because I define G like this, and then I can use the identity, but this is also equal to, I can move this guy to the other side, bar beta dot. Okay, this is by the by this identity here. Okay. So now we just have to open and see what we get. So let me recall what these functions are. So let me maybe copy this. Just for the moment, let me put this guys here on the bottom, just so you can look and recall what these functions are. Okay. So we do have this identity now, which is this guy here. What does it implies? So let's see. Well, the first is T alpha. So what I'm doing is Z minus alpha bar, Z minus alpha times this guy, which is KWZ. KWZ minus K alpha Z, KW alpha divided by K alpha alpha. And then this is K beta Z, the second function there, beta Z, and then with alpha bar. Yes, and then this is K alpha bar, alpha bar. That's the inner product we have. That's the first one. So this is this guy here. This is this guy there. Okay. And that's supposed to be what? So let me just compute what this guy is, and then I compute the second. So first I will compute what the result of this thing is, and then I will compute the result with what this thing is. But then note something. Note that if I compute this, I pretty much also have computed the other, because the other one is just, I do bar on the first. It's just the same computation, but I just do bar on the first. So I swipe this first term with this other one. And then I change alpha by alpha bar. So I get an alpha here. And I change W by beta. So if I compute the first, then I compute the second as well. Okay. So what is this guy? Well, let's see. So I have a bunch of reproducing kernels here, so it should be easy. It should be just evaluation at some point. So if I do this first guy with this one, I would just evaluate this guy here in beta. Okay. And the second one, which would be this bit times this whole thing, I'm integrating, I'm doing this in the variable z, so I should put here the variable z here. Just to note that I'm doing the inner product in the variable z. And in here, the only term that depends on z is this guy, and so it should be evaluation at alpha bar, but this whole function here vanishes at alpha bar because we have this multiplying term. Okay, so it's just, so this bit would just be this guy times this, and I would just evaluate this bit at beta. So let's evaluate. So we get beta minus alpha bar, beta minus alpha, k with w beta minus k alpha beta, k w alpha, k alpha alpha. Okay. So then, so this is the evaluation of the first. If I evaluate the second, should be just equal to, let me move this thing a bit down here. Okay, so if I just evaluate the second, as I said, it's just, I change beta by W and alpha by alpha bar, but then I conjugate everything. So it should get alpha bar here, so this doesn't change, then this doesn't change, and then we should swipe beta by W and then conjugate everything, and then swipe beta by W, conjugate alpha, conjugate everything, swipe beta by W, conjugate alpha, conjugate everything, and then it should be alpha bar bar, everything bar. Simply because, again, this computation is exactly as the other one, but just changing alpha by alpha bar, beta by W, and then you conjugate the whole formula. Okay, so now I can, so this is the identity we have. Now I can erase this guy here. Okay, so that's the identity we have. But I want to put exactly as the identity in the book. So one more thing we have to note is that, well, KWZ, should write that. So note that KWZ bar is what? Is, well, KWZ is just this bar, but bar is just this, but this is KZW, okay? It's a very simple identity to show. So KWZ everything bar, you just flip W with Z and you get the function. So we'll do that in here. So that would be KW beta minus, and then here is just W alpha bar, and then in here is just alpha bar beta, and then in here is just, well, this guy knows K alpha alpha is always positive when alpha is non-real. So doing bar or not doesn't matter, this thing is real. So I could just write K alpha bar. Okay. So then we get this identity here. I should use another color. Let's see this. So then we get this identity here. This equals that. Okay. This thing here. Okay. So exercise, and this is just a computation. This, you have just to write everything in terms of L now. Then using that KWZ equals, by definition, LWZ divided by 2 pi I W bar minus Z, okay? So this is exactly identity, which I called identity double star, I guess. Let's see. Double star. Go back to green. Oh, this is too green. This is the green. This is exactly identity double star. Okay, so you just write this identity in terms of L. Okay, so that finishes the proof. Okay, so let me just recapitulate the proof, and then I can ask if you have any questions. So the main part is to apply problem 52 and 53. They say that whenever you have this identity plus is another identity for L, which is this big one, then K has the form we want for some repeat function. And then from that, it's easy to deduce that the spaces are equal. Okay, and I did that before as well. Okay, and so this first identity I showed, which was this bit here, which came from hypothesis 3, this one here. The other one has to come from hypothesis 1, okay? And how we show that? Well, the main idea is to first prove this statement here, that the adjoint of T alpha is T alpha bar, where T alpha is this operator here. So that is to prove that this is true whenever you can apply the operator in U and you can apply the operator T alpha in V. That is whenever U of 0, alpha is 0 and V of alpha bar is 0. So once you have this, you have to apply it for certain auxiliary functions, which would be this function F alpha W Z. And I will apply to this function and compute the inner product between F alpha bar and T alpha of F alpha, which is what I did here. So the inner product between these two creatures is, is just the inner product between these two guys. And I know by the identity should be this. And you just open the calculation and see what you get. You get in the first this bit, and you get in the second this. And then by using this third identity here, which is satisfied for any reproducing kernel Hilbert space, you see whenever you do bar, you just flip the entries here in the cardinal, whereas in general, doesn't assume anything. So I use that in here, and you come up with this identity. And my claim is that this is exactly what we want, the double star, if we just replace everything by this bit here, okay? So then finally we can apply problems 52 and 53, which are the difficult ones. I mean, the difficult part, one of the difficult parts in the proof, but it's not hard to do it, okay? Again, take a look in the LP spaces, how we did it there, and then try to mimic some of the proof, but not everything, because you need some extras ideas. Okay, any questions here? Okay, great. So this is the last class for this year. We'll continue next year, and next year we probably will do a bunch of applications. I want to do, hopefully, I want to do some other applications in number theory, and I also want to present the paper of the Branges, which has an approach for the human hypothesis using this, and also how it fails, because it fails to work at least in two cases, for the Riemann zeta function and for another L function. But it's a very nice strategy, and it's which I want to present as well. So I'll probably do these two things, and if we have time, maybe some other things. Okay, and I hope you enjoy it, and so see you next year. Bye-bye.